by the science guy.
Good morning and welcome to the wonderful world of physics. Today we'll be going over to Prairie View A&M University in Texas to visit a very wonderful professor. He has the magical ability to show his work as he's speaking. So let's pay attention to what's going on in Dr. Storr's classroom.
Good morning, everybody. Young Buckies, young Buckets. Hi, who's going to be my leader today? You? Yeah? No? Okay, never mind. I'm very hungry this morning. I got that good taste for, that good old Cracker Barrel. That Cracker Barrel breakfast, Man, today we're going to talk about force and momentum. Say, for example, we have a car. Don't laugh at my car, by the way. And
in this next example, we're going to look at Newton's first law of motion. Newton's first law of motion is also known as the law of inertia. I can't spell inertia. It states that an object in motion remains in motion unless acted upon by an unbalanced force. In this case, the video shows a car driving. What an awesome car. With a box on top of it. The car is proceeding in a forward motion until it hits the brakes. Once the brakes are applied, the box will remain in motion. The brakes only apply to the car, but not the box. That's Newton's first law.
What are they doing tomorrow?
talk about how, say for instance, we're throwing a ball off of a building.
Okay, so in this experiment that we're seeing here, we theoretically have a 4-kilogram ball and a 1-kilogram ball falling from 36 feet. So Newton's law says that the force exercising on an object produces an acceleration of A, such as force equals mass times acceleration, where mi is the inertial mass of the object, so this at a rest. On the other side, the force is the gravitational force of the weight, P, which is P equals mg times g gravity, where mg is the gravitational mass and g is the gravitational acceleration. This equivalence principle says that the inertial mass and the gravitational mass are equal to each other. So mg is going to equal mi. So you have force equals P, which that is equal to mg g times MIA. But mg equal mi, so that the acceleration is equal g, and this does not depend on the mass. So in the experiment that we did, theoretically, these two balls would fall in free fall at the exact same time and hit at the same time. But when we actually did the experiment, the larger ball fell first and bounced higher than the lighter ball. And that is because we have to count on air resistance. Usually in Physics 1, we ignore air resistance when doing our free fall problems. So that's all for the wonderful world of physics in Dr. Storr's class at PVAMU.
Tune in again for a wonderful world of science. Bye-bye now.
Bill Nye the Science Guy.